We have a question. All right. Let g of xy be a twice differentiable function. We have some information. G of 2, 1 is 0. G sub x of 2, 1 is 0. G sub y at 2, 1 is 0. Lots of zeros. Gxx of 2, 1 is 4. Okay, good, not 0. Gxy at 2, 1 is negative 3. Gyy at 2, 1 is positive 6. Using all of this information, what is an estimate for g of 2.1, 1.2? All right, so we have some options, 0.06, 0.08, 0.12, 0.20, 0.22. What's the answer? B. Good. B is the correct answer. Now you might say, well, wait, aren't all of these estimates? I mean, why is 0.08 the answer? Well, 0.08 is the answer because it's using the derivatives in the sense that it's basically saying, let's do the Taylor polynomial. Now, because we have lots of zeros, and this is a time when zeros are your friend. Actually, 0 is always your friend other than, an exam score. But we like having zeros in computations. It makes things simpler. So the only part that's affecting it in terms of the Taylor polynomial are the second order terms. So it says g of xy is, a bunch of zeros plus, then you have your second order terms. And don't forget these 1/2s here. These 1/2s are important. And so since we know these derivatives, that's easy. We can also figure out delta x is 0.1, delta y is 0.2, so we can put in those values, and then we compute. So 0.08. So that is our best estimate using that information. Because in essence, when we talk about Taylor polynomials, it's the best polynomial that mimics the function nearby. That's what Taylor polynomials do. It's always trying to say, what's the best polynomial?
Why doesn't the partial x, partial y have a 1/2 in front of it?
Well, for one thing, we don't have a partial x, partial y in this expression. But the question is that we should think about is where is that 1/2 coming from? Why do you have it? So the simple answer, I don't know if it's simple, but this 1/2 here is in response to that 2 there. So what happens is when you're taking a derivative, that 2 will come down, and you want to end up not with 2gxx, you want to end up with only gxx. So you have to have something that cancels that 2 out. So you have a 1/2 in the front. On the other hand, if you don't have a power of 2, so notice here, these are to the 1 power. So as you're taking those derivatives there, you're bringing 1s down. And since you're bringing 1s down, you're like, 1's okay with me. I'm okay with this. Now, we didn't talk about it, but we could, if we were so inclined. We have space. We can fill stuff up. What if we wanted to do a third order Taylor polynomial? Is such a thing possible? Yes. What would it look like? Well, I would say g of xy, just word of warning, there's going to be a lot of writing here. All right, you've been warned. The 0th order term, the value of the function. The 1st order term, the value of the derivatives. G sub x, ab, x minus a, g sub y of ab, y minus b. Then we go into the 2nd order term. So gxx, ab, I know, don't worry, I left a suspicious gap there. X minus a squared. And just think about how would I take derivatives to get this x minus a squared to be a constant? Well, I take 2 derivatives with respect to x. In the process of taking 2 derivatives with respect to x, I'd create a 2. So put a 1/2 here. So that at the end, you'd end up with just the gxx. Then you have your gxy, ab, x minus a, y minus b. And you say, okay, what would I do to make the x minus a, y minus b constant? Well, I take one derivative with respect to x, one derivative with respect to y, and I'd end up with a 1. So how do I compensate for the 1? I don't have to. I like 1. 1 is my other friend. I have 2 friends, 0 and 1. You're allowed to have more than one friend. It's true story, true story. Okay. So then we have our other term, and just in the interest of time, I'll just say it's gyy, ab. Okay, great. Now we get to third order terms. So, suspicious gap, g, x, 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 a, b, x minus a cubed. What goes in front? 1/6, good. Why the 1/6? Because you're going to have to take 3 derivatives. You're going to bring a 3 down. Then you're going to bring a 2 down. And then you're going to bring a 1 down. All right. Now your next term will be a g, x, x, y, ab, x minus a squared, y minus b. What goes in front? 1/2. Because you're going to have to take 1 derivative of y, and that's okay. You have to take 2 derivatives with respect to x, you have to bring a 2 down. All right, how about for the g, x, y, y? Can you figure it out before I finish writing it down? What will be there? Another 1/2. Plus, you have g, y, 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 ab, y minus b cubed, and what goes here? 1/6. So that's the third order. Could we do fourth order? No, we don't have enough space. But more to the point, we kind of see the pattern that's going. And so if we had to, we could write it down. All right. Anything else? Good. So there's a quote here. We don't actually know who it's from, but it's often attributed to Thomas Jefferson. But it's a fun quote regardless. I am a great believer in luck, and I find the harder I work, the luckier I get. And I like this. I also am a great believer in luck. In many ways, yes, my success, you could say, is I worked hard at my job, and that's true. But I can also point to just a couple of moments in my life where it's like, I was really lucky. And if that event had not occurred, I'm somewhere teaching high school. For example, when I was applying to graduate school, first time I applied, nobody let me in. The second time I applied, I got in to 2 places. And the 2 places I got into were places where the people who were on the committee who made decisions about whether or not you got in were very good friends with the person who wrote the letter of recommendation for me. And so that letter got me in. That was some luck involved, which, by the way, you should learn to get to know people. The more you can network, the better you are. And you might think, I'm super bright. Of course people are going to come and beat a path to my door. No, they're not. You got to know people, and you got to use the people that you know in a friendly way. I'm not trying to say in an unfriendly way. And then in a second time, when I was in graduate school, I almost switched to a different graduate school in a completely different field. And I was like literally hours away. And then the person who became my PhD advisor said, come talk to me. If that hadn't happened, I wouldn't be here. So, you know, there's a couple of events in my life that I say, yeah, I was very lucky. But you have to have a combination of the two. And another thing I often think about is that luck is sometimes about perception. A lot of people who say, oh, I got lucky, is more along the lines of they were like, oh, I saw an opportunity or I saw an idea. So I think being lucky, a lot of it is a case of have your eyes open to opportunities and be ready to take those opportunities. And you might say, well, how do I learn to have my eyes open to opportunities? Say like on a math problem. How do I get lucky in a math problem? You do lots of math problems. And what happens is you say, oh, I'm seeing patterns emerge so that I can see similar patterns in the future. And you're like, oh, I got lucky. I did a similar problem like this last week. I'm going to do great on this exam. That you can make a lot of your own luck. All right. So that's for today. So, what's today? We're going to talk about optimization. And in fact, I'll tell you that I've already mentioned there's 3 lectures left of material before the exam. Today, we're going to talk about optimization. Next time, we're going to talk about optimization. And the time after that, we're going to talk about optimization. So like everything between now and the exam that we haven't covered yet is about optimization. But we have 3 flavors. So first off, we have to talk about what is this optimization thing that you've mentioned. So when we're talking about optimization, we're talking about maximums and minimums. We're trying to find the best. So this is, in some sense, you could say this is a part of the course. This is the ist part of the course. We want the highest, the lowest, the fastest, the smallest, the largest. We're trying to just extract as many resources as we can. Now, generally speaking, there's 2 kinds of maximums and minimums we talk about. So the first kind are what we call absolute. So you have an absolute maximum at a point if your function at that point is bigger than or equal to the function anywhere else. So in other words, it's the largest value that's obtained. That's an absolute max. And by the way, absolute is sometimes called global. So you might hear it called as a global max. And then, of course, the other side is an absolute minimum. So an absolute minimum says, I am the smallest value that the function achieves. No other point is smaller than me. So every other point is greater than or equal to the value of that function. Now, we know that only the Sith deal in absolute. So there's another type, which we can call relative. So a relative maximum, and relative can also be called local, and almost always we call these local. A local maximum, or relative maximum, at a point AB says, I am the largest point of the points nearby. So in other words, if I look in a very small neighborhood, and remember calculus, we're really good at understanding things in a very small, like nearby, what's happening. That's what calculus is doing. So nearby, I am the largest point. I'm a local minimum if nearby, I am the smallest point. So there's nothing near me that's smaller. There could be things that are smaller that are far away from me. That's okay. I only care about what's happening nearby me. So those are our 2 things. We have our global max and min, and we have our local max or min. All right. Well, what's the question? How do we find these? Oops. So here's an idea. Now, if you sort of channel your inner single variable calculus life, you'll say the way we would find these points, what would you be looking for? Slope equals 0, derivative equals 0. So we're basically going to say, can we channel the same thing? So we say, okay, well, what's taking the place of derivative or slope? The gradient. We think about the gradient. Now, the gradient does what? It's pointing the way to go uphill as fast as possible. Negative the gradient points the way to go downhill as fast as possible. So here's an observation. If the gradient isn't 0, now what that means is, if the gradient isn't 0, gradient equals 0 means that you're flat. So if the gradient isn't 0, it means you're tilted one way or the other, or some combination. So if the gradient isn't 0, you're on a tilted plane locally, you can move and you can go up. You can move opposite the gradient and you can go down. So when the gradient isn't 0 and you have that freedom of motion, you can't be a min and you cannot be a max because you can do better. Okay, so that rules a lot out. So what's not ruled out? What's not ruled out are what we call the critical points. So critical points are where the max or min can occur. So they fall into more or less 3 categories. And they are, the gradient of f is 0, because then that doesn't hold, namely the gradient of f being non-zero. The gradient of f is undefined, again, the gradient of f being non-zero. Or a boundary, because boundary is where you don't have that freedom to move. So what's happening at a boundary, it might be saying, hey, the gradient says you should move in that direction to increase. But the boundary says, no. You're at the edge. You cannot step anything in that direction. Now, for today, we are going to talk about this case. That's our case for today. Gradient of f equals 0. We are not going to talk about gradient of f being undefined, because essentially that doesn't come into play. Next time, we're going to talk about this case. That'll be a fun time. Good times, good times. All right, so we now know intuitively where max mins should occur. Gradient should be 0. That's the punchline for today. So let's try this out. Any questions about the idea? Okay. So find all the critical points for the function f of xy equals 3x cubed plus y squared minus 9x plus 4y. Now, in relationship to what we just talked about, is there any boundary to this? Just want to be clear. Yeah, no. Boundary would be like on the region where you have, x goes between 2 and 4. That's the kind of thing when you see boundary. So there's no boundary here. This is a nice function. Will the gradient ever be undefined? No. So critical points boils down to saying, we need the gradient to be 0. All right. Well, that's good to know. So let's work on that. So gradient of f equals 0 really boils down into 2 equations. We need f sub x and f sub y. So what is f sub x? 9x squared. Anything else? Minus 9 equals 0. F sub y? 2y plus 4 equals 0. We now have 2 equations and 2 unknowns. And by the way, if you're worried that we're going to ask you to find critical points for f of x, y, z equals 0, we're not. We don't have that. We'll explain why in a few minutes. That is a type of a problem, but we're not giving you the tools to explore that for important reasons. All right. So, 2 equations, 2 unknowns. That sounds really familiar. I will warn you, they can be very interesting equations. So we have to be ready to use lots of different tools to solve these. Now in this case, our first problem, we're warming up. So, is there anything we can do here? Any ideas?
Algebra.
Oh, algebra. Bold move. I like that. So in this case, it's not going to be too surprising. How about this equation? 2y plus 4 equals 0. What is that going to tell us? Y equals negative 2. Okay, so you could, for example, say 2y equals negative 4 and divide, say y equals negative 2. A lot of people can just see it right away. How about this other equation? 9x squared minus 9 equals 0. Oh my goodness. Okay, you could factor out a 9. Then you can, of course, factor that into x minus 1, x plus 1. There's lots of ways to see this, which leaves you with either x equals 1 or x equals negative 1. So how many critical points will we end up having here? I've heard 1, 2, 3, and 4. One of those is probably correct. So keep in mind, both equations have to be true. So this tells us our critical point has to have the y value be negative 2. This one tells us we have to have the x value be 1 or negative 1. So that gives us two possibilities. 1, negative 2, and negative 1, negative 2. And that's the critical point. That's all of them. There's no others. So 2. All right. So finding critical points, take the partial derivatives, set it equal to 0. Solve. And we'll get more practice. We'll get good at it, or at the very least, we'll get better at it. Okay. But that's not quite the end of the story. There's a question. We started by talking about minimums and maximums. So the next thing to ask, are either one of these a minimum or a maximum, or maybe something else? So now we'd like to talk about classifying. So that's our next goal. So let's talk about classifying critical points. We know how to find critical points, set the gradient to 0. How do we classify? So let's see if we can remember things from our good old days of single variable calculus. Only one variable. So easy back then. Okay, so do you remember a test to say if something was a max or a min? What was maybe the first test you learned about? Yeah, first derivative test, right? Okay, great. That was pretty nice. In fact, the first derivative test had a lot of great stuff going for it. It was pretty intuitive. So for instance, if you had a critical point C and you said, oh, f prime is positive beforehand, f prime is negative after, that told you something. It said, hey, the function's coming up, the function's going down. Because positive negative tells you, are you going up or down? And then you said, hey, this says something about C. What does it say C is? It says that C is a max, right? Or you may have had something like this, where you had C, and you said, oh, it's negative, and then it's positive. Then what's going to happen at C? It's min, because you're going down, and then you're going up. So it's a min. And we'll do one more. There's a total of 4 possibilities. What if, say, you were negative and then you were negative again? What did you have? You went down, and you went down. So you had neither, right? That was basically the flavor. Okay, so that's cool. So you say, all right, well, that seems like a pretty nice test. We take our critical point and we say, what's happening? So what happens for multivariable calculus? What does this become? This becomes nothing. There's a problem. If you're in single variable calculus, how many directions can you be approaching from? 2. If you're in multivariable calculus, how many directions can you be approaching from? Infinitely many. So you can test, say, there's like 18 different directions I tested, and in all of them, it looks like I'm at a maximum. Does that mean you're at a maximum? No, because you maybe are not looking at it from the right direction. So the problem is there's too many directions to test. And there's just no way to do this using the first derivatives. Too many directions to check. All right, well that's disappointing. But that's okay, we've got space. All right. Now, by the way, in case you're wanting an example, I'm not a good artist, but the computer can do this. So there's this function here, 4x to, well, it doesn't show up well on the screen, but 4x to the fourth minus 17x squared y squared plus 4y to the fourth. If you go along the axes, it looks like you're at a min, but if you come along the lines x equals y or y equals minus x, it looks like you're at a max. So it shows you that it really does depend on which directions you test, that whether it looks like a min or a max. So you have to be careful. That's why we tell you be careful. Okay, well that, was there another test that we learned in single variable calculus? Was there maybe a second test that we learned? Yes. Yes, there was a beautiful test called the second derivative test. Okay, good. Second derivative test. Do you remember what the second derivative test tells you? Derivative, I can spell derivative. Okay, it tells you about concavity. Good. Now, what does concavity tell you? It tells you whether you're like concave up or concave down, right? So concavity tells you about the concavity, Steve. You know, because concavity is concavity. So here's how I think of it. Just in general about the second derivative. And then I'm going to talk about it in particular for the second derivative test. So if I have a line, say this is a tangent line, and I have a function. If I'm concave up, this is my point of tangency. Concave up is asking the question, how does the function come off the tangent line? Because the tangent line is an approximation. Concave up says I'm coming up on the upside. Concave down says when I come off the tangent line, I'm coming on the downside. So that's concave up versus concave down. So how does this relate? Well, when we're at a critical point, our tangent lines are flat. So concave up says locally we look like this, and concave down says locally we look like that. Now, in terms of the signs, concave up, is that associated with a positive or a negative second derivative? Sorry, what? Positive. Good. So this is second derivative positive. Here, this is second derivative negative. Now, what happens if the second derivative is 0? That's right. Good answer. We don't know. Wonderful non-response. So the way I remember the second derivative test as a picture, if the second derivative is positive, we locally look like that. So we're at a min. If the second derivative is negative, we locally look like that. So we're at a max. And if our second derivative is 0, we channel the portrait of the scream. We don't know. We don't know. All right. So those are our cases. So second derivative tells us how we come off the tangent line. Is there something in multivariable calculus for that? The answer is yes. It's called the second partials test. Okay. So there is a way to use information about the second order derivatives to make a conclusion about what's going on. So how does this work? Well, Now we have to go back to our last lecture. And you might remember at the very end, we threw up a matrix. And we said, oh, if gradient of f is 0, then what happens is that f of xy is behaving like f of ab plus, then there's this delta x, delta y. This, I'm going to suppress the evaluations, fxx, fxy, fxy, fyy, delta x, delta y. So if the gradient is 0, we're behaving in this way. We can write it in this way. So this matrix, which is composed of second order derivatives, is driving behavior. And here's the punchline. This will tell us how we are coming off the tangent plane. Just like the second derivative tells us how we came off the tangent line, this tells us how we come off the tangent plane. So, how does that happen? Well, it turns out, I don't know if I'm going to be able to squeeze all this in to this space. Time-wise, we definitely won't make it, but space-wise. Okay, all right. Here we go. It turns out that there's a pair of numbers called the eigenvalues. So I'm waving my hand right now. If you've had linear algebra, you're like, ooh, eigenvalues, that's awesome. If you haven't had linear algebra, you'll be like, that sounds German. And you're right, it is German, eigen. But the key is there's two special numbers that are associated with this, lambda 1, lambda 2. And what happens if lambda 1 and lambda 2 are both positive, then when we come off the tangent plane, we come up on the positive side. So we're coming up on the top side. So we look like a bowl coming up off the tangent plane. If these numbers are both negative, and then what happens is we again look like a bowl, but now we're not going up off of the plane, we're going down. So we're an upside down bowl. And then there's one other case. Let's say lambda 1 is positive, lambda 2 is negative. So in other words, they have different signs. Now this is sort of a strange case. But what it says is that in one direction, you're going up off the plane. But in a different direction, you're going to be going down off the plane. So you have sort of different behaviors in different directions. And then what kind of shape does this mimic? Saddle. So we have essentially our three cases here. Now, how do we figure out these cases? Well, the good news is you can find out what happens if you multiply lambda 1 times lambda 2. So there's a function which we call d. And I know we've used d before for derivative. This is now d for discriminant. Or you could call it d for determinant. But it's d. We have to recycle. That's all right. We're environmentally friendly. So d, which is this lambda 1, lambda 2, which is 2 by 2 determinant, fxx, fyy minus fxy squared. So you compute that value. So compute d at your critical point. And there's three cases. So if d is negative, what does that tell you? Saddle. Why does it tell you saddle? You're right, it does tell you saddle, but why? Yeah, you have one positive, one negative. So if you get a negative value out of this expression, now you don't care about the value so much, you just care about the sign. Just know enough to know the sign. So if it's negative, it's a saddle. Okay, if it's positive, then what? It could be a min or it could be a max. Because if you multiply two positive numbers or you multiply two negative numbers, you still are positive. So you're going to go deeper down the rabbit hole. Don't worry. When we say go deeper down the rabbit hole, we say at this point we know for sure we're a min or a max. So here's the idea. If I know I'm at a min or a max and I take a slice, what's true about that min or that max? If I'm a min and I slice, am I still a min? Yes. If I'm a max and I slice, am I still a max? Yes. So if I'm a min or a max, I just have to look in a slice, and I'm still a min or a max. Now you might say, why look in a slice? Because we have a test. We're back down to single variable test. So what does the test say? Well, look at fxx. Now, if fxx, so we're back in single variable, what happens if that's negative? Min or max? Max. What if fxx is positive? Min or max? Min. So we go back to our second derivative test. We're taking the second derivative test in the slice. Now you might say, do I have to use fxx? No. What else could you use? fyy. Either one, they'll both give you the same answer. They'll never contradict each other. So use whichever one is easiest. What happens if you get 0? Then you give up. Actually, that's not quite the phrase we say. The phrase we use is inconclusive. But if it's 0, we don't have enough information to make a decision. So that's the test. So you find your critical points, you plug your critical points into this expression, and then you use the rule here. Check the signs. So you can tell if it's a saddle, a max, or a min. Almost never will give you something where you have a give up, but in theory, it might happen by mistake. All right, I think we have time to do one, maybe two if we go at a good clip. Okay, what's the most interesting one? You look interesting. Any questions about the test? Now, they love this test. Be ready for it. They love optimization in general. So, be ready for optimization. All right. Find and classify the critical points for the function f of xy equals x squared y plus x squared minus 6xy plus y squared minus 6x plus 7y. All right. Nice, simple function. It's the kind of function you'll see all the time. And all these problems are going to be very familiar. We're always going to give you a function of two variables. And I didn't point this out. Why would we give you functions of two variables? Can't we do this for three variables? The thing is that the second partials test, the way we've written it here, works because you have a 2 by 2 matrix. You could do it for three variables, but then you'd have a 3 by 3 matrix, and it gets a lot worse. So we're not going to do the XYZ problems that have this form. So there's always two variables. It's basically 99% of the time, it's polynomial. All right, so step one, you always start with the find. You can't classify what you haven't found. What do you need to do the find? Find critical points, which means we do what? Set the gradient equals to 0. So in particular, I just go straight to the partial derivatives. fx, and in interest of time, I'm just going to say things out loud. 2xy plus 2x minus 6y minus 6. Fy is x squared minus 6x plus 2y plus 7. Those are our partial derivatives. We now have two equations, because we set both of them equal to 0, and two unknowns. Okay. Two equations, two unknowns. How do you solve? Well, when you're looking to solve, you're basically going to have your two tools, which are factoring and substituting. Those are your two go-tos. If you can, factoring is always preferable. So always try to factor first. If you can't factor, then you start looking for substitution. Now, sometimes factoring is a little bit more obvious. We use factoring in the first problem. Sometimes it's a little less obvious. You have to think about it a little bit more. So we're going to ponder for about 3 seconds. And we're going to say, there's a factoring that goes on, because we have to finish before time expires. Does anyone see which one factors? The first or the second one? Yeah. Good. So if you take the first two terms, oftentimes think of like just sort of clumping. 2x, then you get a y plus 1. And then you take the second two terms, minus 6, y plus 1. So then you say, well, this looks like 2x minus 6 times y plus 1. And why do we like to factor? Because it lets us break it into smaller pieces. If 2x minus 6 times y plus 1 equals 0, one of them had to be 0. So either 2x minus 6 equals 0, or y plus 1 equals 0. It's not that both are 0, but one of them has to be 0. 2x minus 6 equals 0. What's another name for that? X equals 3. Y plus 1 equals 0. What's another name for that? Y equals negative 1. Okay, so we have two options to explore. Doesn't matter. Let's start with the x equals 3. We plug x equals 3 now into the other equation. So doing that, we'd have 9 minus 18 plus 2y plus 7 equals 0. So we're doing the x equals 3 into the other equation. 9 minus 18 plus 7 gives us negative 2. So 2y minus 2 equals 0. So y equals 1. All right, so what's our critical point? X equals 3, y equals 1. Okay, so we found one critical point so far. And by the way, you could get lots of critical points. So it's not like, two equations, two unknowns, I'm going to get 1 point. You can have 5, 6, 7 points. We sometimes come up with problems with a lot of critical points. Okay, so y equals negative 1. Now we go into that same equation and plug in negative 1. So you get x squared minus 6x minus 2 plus 7. Minus 2 plus 7? Plus 5. Well, x squared minus 6x plus 5 equals 0. Does that factor? Yes. X minus 1, x minus 5. Leading us to, again, two possibilities. X equals 1 or x equals 5. But remember, we also are already in the y equals minus 1 case. So that gives us the points 1 comma minus 1 and 5 comma negative 1. Okay, are we done with our critical points in terms of finding? Yes. We've exhausted everything. So these are our critical points. But the problem is only halfway done. What else do we need to do? Classify. Classic. Okay, so we need to classify our critical points. Cool. So, what's the next thing for us to compute when we start classifying critical points? Second derivatives, because it's the second partials test. The only classifying tool we have is the second partials test. So we say, look, we've got our first order derivatives. So we start writing second order derivatives. f(x)(x). Taking derivative with respect to x. Derivative of 2xy with respect to x, 2y. Derivative of 2x, 2. Derivative of 6y and minus 6 are both 0. fxy. Derivative of f sub x with respect to y. You could also do fy with respect to x. You'll get the same answer either way. Derivative of fx with respect to y. Well, you'll get 2x from the first term. That goes away, the 2x. Derivative of negative 6y will be minus 6. That goes away. fyy. So take the derivative of f sub y with respect to y. Get 0, 0, 2, 0. All right. By the way, I now claim there are no maxes here. Is that true? There cannot be a max?
Yes. Yeah.
Yes? And the reason is fyy is always positive. If we had a max, fyy would have to be negative. All right. Well, so cool. So now, with these, we construct our function d. That's the fxx fyy minus fxy squared. So 2y plus 2 times 2. Subtract 2x minus 6 squared. We need to plug in each point. Okay, so let's start with 3, 1. 2 times 1 plus 2 is 4. 2 is 2. 6 minus 6 is 0. Is this positive or negative? Positive, it's 8. But I don't care about its 8-ness, I care about its positiveness. Okay, max or min? Well, we know it's one of them. The correct answer is yes. And then you say, oh, okay, but now look in the slices. fyy is positive. Also, fxx is positive at that point. So this is min. Okay, plug in 1, negative 1. All right, we get minus 2 plus 2, 0, times 2, minus 2 minus 6 is negative 4 squared. Is this positive or negative? Negative, right? This negative 4 squared is going to become 16, so it's really 0 minus 16. Be careful about where that negative goes. So what does that tell us about 1, negative 1? Saddle. Negative here tells us saddle. How about for 5, negative 1? Well, again, 2 times negative 1 plus 2 is 0. Hard to recover from a 0. Subtract. 2 times 5 is 10, minus 6 is 4. Squared, positive or negative? Negative. So we have a saddle. And there we've finished our find and our classify and our class time. So we'll stop here for today.